Hi, this is Tzvi Rosen. Today we'll be talking about Artin rings or Artinian rings. Last lecture we spoke about Noetherian rings, which had a lot of really nice properties. This lecture we'll see that every Artinian ring is Noetherian, while the reverse is not true. Artinian rings are a very special case of Noetherian rings. So why is there this asymmetry? Why is it that Noetherian rings are not necessarily Artinian, but Artinian rings are necessarily Noetherian? And I think what it comes down to is the kinds of operations that you can do on ideals. So given a finite collection of ideals, let's say it's A1, A2, etc., AN, all contained in a ring A, you can produce very easily ideals that are contained in these ideals. So for instance, AK squared is contained in AK. Right? So if you take the square of an ideal, that's a smaller ideal inside of your original ideal. And furthermore, you can make a whole chain saying AK contains AK squared, contains AK cubed, etc. Okay, so this is a very natural chain, a descending chain of ideals in your ring. Similarly, if you have, given any pair of ideals, AI and AJ, AI times AJ is contained in both of them. So this is contained in AI and AJ. Okay, so if you have, let's say you have an infinite collection of ideals, you could, so in the case where, let's give this a little parentheses. In the case where you don't necessarily need this list to terminate, you could have a chain that looks something like A1 contains A1A2, contains A1A2, A3, etc. Okay, so these are all very natural constructions that give you a descending chain of ideals. And what the Artinian condition tells you is that those have to be stationary. So at some point, you run out of room at the bottom. Okay? Artinian means that these chains, which arise very naturally, must be stationary. So that's imposing a lot of conditions on our ring. If all of these chains of ideals that occur naturally have to be stationary. On the other hand, constructions producing inductively larger ideals are not common. Okay, and you can take a radical produces a larger ideal, but you can only really do that once. You can add ideals, but that often runs into the problem of just sending you to the whole ring. So these constructions, the constructions that give you larger ideals are not going to be super useful to impose a lot of conditions on a Noetherian ring. So while you have these very natural constructions putting conditions on your Artinian rings, and thus constraining what they can be, Noetherian rings, the Noetherian condition does not place the same kind of natural constraints. Okay, so hopefully that gives a bit of an intuition for why we have this asymmetry, and now we can get to the rest of the talk. We're covering Chapter 8 in Atiyah-MacDonald. So we'll start by talking about the prime ideals in Artin rings, then Krull dimension and its relationship to Artin rings, and finally we'll look at Artin local rings. So that's the Artinian rings that have a single maximal ideal. Let's get going. Okay, we'll start by proving that every prime ideal in an Artin ring is maximal. So let A be an Artin or Artinian ring. I think we take off the IAN just because it's a little bit of a tongue twister. That's my guess for how this notation developed. But in any case, we have an Artinian ring, and we're taking P in A prime ideal. Then P is maximal. So how do we prove this? So we're going to consider the ring A mod P. Okay, so whenever you mod out by a prime ideal, you get an integral domain. Okay, you also get that this is Artinian because you have this exact sequence of A modules, starting with 0, mapping to P, then to A, then to the quotient. Oops. Back to 0. That gives you, when you have an exact sequence where the central module is Artinian, that tells you that on either side they're also Artinian. So this means that A mod P is Artinian. So now we know it's an integral domain. Artinian. We know it's an integral domain, and we know it's Artinian. So we're going to consider a random element, an arbitrary element in this ring. Okay, so we're going to have a chain of ideals, and we're assuming this is not equal to 0. So we have a chain of ideals, the ideal generated just by x, which contains the ideal generated by x squared, which contains the ideal generated by x cubed, etc. So this must be stationary by the Artinian condition. Given this stationary sequence, that means that there's some index n with x to the n equals x to the n plus 1. But what that means is that I can find x to the n in the second module. That means that x to the n equals a x to the n plus 1, where a is some element in the ring. And that tells me that x to the n times 1 minus ax equals 0. Okay, obviously we know that x to the n is not equal to 0 because we're in an integral domain. So that means that 1 minus ax has to be equal to 0. Okay, so since this is an integral domain, we know that ax equals 1, which means that x is a unit. So taking an arbitrary element in the quotient ring by P, we find that it's a unit. If every x not equal to 0 is a unit, that means that that A mod P is a field, which by the correspondence theorem means that P is a maximal ideal. Okay. So for an Artinian ring, every prime ideal is maximal. Okay, and an easy corollary of that is that the nil radical is equal to the Jacobson radical, because we'll recall that the nil radical, this is equal to the intersection of all prime ideals, P prime. Okay, and since every prime ideal in an Artin ring is maximal, this means that this is equivalent to P maximal. for Artin rings. Okay, once you have that this is equal to the intersection of maximal ideals, well, that's exactly the definition of R, the Jacobson radical. Okay, so this is just a straightforward consequence of the fact that every prime ideal is maximal. But we can go even further than that. We can say even more. An Artinian ring actually has only finitely many maximal ideals. So let A be an Artin ring. A has finitely many maximal ideals. And we'll prove it as follows. So consider the set of maximal ideals. It could be finite. We'll index them by some set. So mi, I in I, not necessarily, we're taking that to be the index set. It doesn't have to be finite yet. This will be the set of finite ideal, the set of maximal ideals of A. Take the set of finite intersections of the maximal ideals in here. So take the set of finite intersections and it'll be subsets of this which are finite of the mi. I will be in J. Okay. This is obviously a finite collection of A modules, or of ideals, so this will have to satisfy the minimal condition. So by the fact that A is Artinian, this has a minimal element. Okay. Given that minimal element, so without loss of generality, we can just call it M1 intersect up to Mn, just by relabeling. Okay, so we'll call this capital M, M1 intersect up to Mn. Now consider what happens when we intersect an intersect a random maximal ideal, an arbitrary maximal ideal, with this module M, or this ideal M. So take M maximal, then M intersect M. Obviously, it's still a finite intersection of maximal ideals, so it should be in the collection we were discussing at first, which means that it has to contain M. So by minimality of M, this is actually equal to M, okay, because M is the smallest ideal that you can get after intersecting maximal ideals, finitely many maximal ideals. So in particular, this means that M contains M, because otherwise you would lose something from capital M when you carried out this intersection. But this, again, unpacking what M is, this means that M contains some intersection of maximal ideals, okay, which in particular means it contains their product. But we have a result that when you have a prime ideal containing a product of other ideals, it has to contain one of those ideals. So this implies that M contains Mi for some I. Okay, and this is because M is prime. And that means that M must be equal to Mi because Mi is a maximal ideal. So if it's contained in some other prime ideal, that's all, that just itself. Okay, so what that tells us is no matter what maximal ideal I pick, it's going to be one of these n ideals. So any maximal ideal of A is in the set M1 through Mn. Okay, so it's a pretty powerful result. We're saying that the Artinian condition on rings tells us that there are only finitely many maximal ideals. And in fact, since all of the primes are maximal, there are only finitely many prime ideals. You can think to yourself what that would mean for the spectrum of that ring. Okay, here's another result proved in Atiyah-MacDonald. The nil radical of an Artinian ring is nilpotent. So let A be an Artinian ring, Artin ring, and we're going to take N to be its nil radical. Then there exists a K such that N to the K equals the 0 ideal. And you might say, but the nil radical is always composed of nilpotent elements, so why is it shocking that the nil radical should be nilpotent? There's a difference between the whole ideal being nilpotent and any particular element being nilpotent. Okay, because even if every element has some exponent for which x to the k equals 0, that doesn't mean that, that those exponents as a set for the entire ideal are bounded. Okay, so this is saying to us we actually have a single exponent that works to send the entire ideal to 0. Okay. Okay, so let's consider the chain n contains n squared contains etc. Okay, this is a descending chain of ideals, which means that by the DCC, this is stationary, which means that there is some element k with n to the k equals n to the k plus 1. Okay. Well, let's name this ideal whatever that value of k is. This ideal where it stabilizes, we're going to call that A. So call this A. And what we really would like is if this A is 0, because then the kth power of n is 0 and we're done. Want to show A equals 0. So we're going to prove this by way of contradiction. Suppose there is, first of all, suppose that A is not equal to 0. Then there are ideals B. Then take sigma to be the set of B such that AB is not equal to 0. Okay? And this is going to be non-empty because if A is not equal to 0, then at least the ideal of the whole ring is gonna make sure that you can multiply by A to not be 0. So this is non-empty because A is in sigma. So by the Artinian condition, we should have a minimal element. Should have a minimal element, so the smallest ideal we can multiply a by, or a smallest ideal, to be fair. A smallest ideal we can multiply a by and still not have it vanish. Okay, we'll call this b. Okay, now consider some element x. So the fact that a b is not equal to 0, this means that there's got to be something inside of b which is not equal to 0, which multiplied by a does not give you 0, right? Because if everything multiplies a to give you 0, then so does the whole ideal. So that means we have some element x in b with xa not equal to 0, but then there's a smaller ideal, or an ideal at least as small, which is just the cyclic ideal generated by x, or the principal ideal generated by x, I should say. So this implies x times a is not equal to 0, which means that x is in sigma, and since it's contained in b, that means that b must just be equal to that ideal, right? Because b was supposed to be a minimal element. So if you have something that's smaller than it, and it's in the same set that we were taking the minimum over, it must be equal to it. Okay, so we have b equals this principal ideal. Going back to consider a, so we'll note that since a is defined as n to the k, which is now equal to all the subsequent terms, you could square a. So a squared is just n to the 2k, which is n to the k, which is just a. So this means that a squared equals a. xa, we already specified, is not equal to 0. And we saw that a is equal to a squared, so we can have xa squared is equal to xa, so that means that this is not equal to 0. But that means that xa, if you take that ideal and then you multiply it by a, that's also not equal to 0, because that's equal to xa squared. But now we're saying that what that means is that xa has to be contained in, or rather, an element of sigma, because it doesn't annihilate a, so it should be in that set. But we know this is contained in b, right? Because xa is obviously contained in the principal ideal generated by x, which is b. So that means that xa must be equal to x. Okay. And if xa is equal to x, that tells us that we can write x as x times a for some a in a. I can multiply both sides of this equation by a to find xa is equal to xa squared. And I can continue doing that inductively to find that x is equal to xa to the n for any n. Okay, but I know that a has to be a nilpotent element because it's in the nil radical. So that tells me that x itself must be equal to 0, which is a contradiction. Okay, so having arrived at that contradiction, we find that the sigma, which we assumed is non-empty, right, the set of ideals not sending a to 0, that's not empty. No, it must be empty, which means that a itself must be the 0 ideal. Okay, and that proves our assertion that the nil radical is nilpotent. Okay, Now let's move to the Krull dimension and discuss the Krull dimension of Artinian rings. So we'll start by defining this. We'll take, so let P0, P1, etc. up to Pn be a chain of prime ideals, which just means that of prime ideals in A. Okay, which means that it's a finite, strictly increasing sequence. Okay, so at no point do you have pi equals pi plus 1. Then about a chain like this, we say the length of the chain is n. Right? It's the index of the largest ideal. Okay, largest prime ideal in the chain. Then we'll say dim A, also called the Krull dimension of A, is defined as the supremum of the lengths of all chains in A, of chains of prime ideals in A. Lengths of chains of prime ideals in A. Okay, so we've proved in the past that every non-zero ring has a maximal ideal. That means that you'll at least get this first prime ideal there. So for A not equal to 0, we know that the dimension is at least 0. You can have infinite chains of prime ideals. So dim A in such a case would be equal to infinity. Okay. When we're talking about the zero ring, there are some different conventions. So let's just not, like either -1 or negative infinity. Let's not go there. In general, we don't want the ring to be 0. Okay, that's the Krull dimension of a ring. And you can convince yourself geometrically, and we'll get to this towards the end of the course, that this corresponds to our typical sense of what dimension is geometrically. So if you're talking about prime ideals related to irreducible varieties in an affine space, then a chain of prime ideals gives you kind of a sequence of containments of varieties of various dimensions, a point into a curve, into a surface, etc., until you get the dimension of the space. Okay. The first thing we can prove is that the dimension of the Artin ring is 0, and that's simple because every prime is maximal. So if you have P0 contained in P1, that means, well, if P0 is prime, that means it's equal to P1. So it's not strictly increasing anymore. So the longest chain we can do is just P0. Okay. But not just that. It's not that the Artin ring has dimension 0. It's that the condition of being an Artin ring is equivalent to being a Noetherian ring of dimension 0. So a ring A is Artinian if and only if it is Noetherian of dimension 0. which is a pretty big result. It's basically saying that Artinian rings are the Noetherian rings of dimension 0, and Noetherian rings are Noetherian rings of any dimension. So it's saying this is the only dimension value that works for Artinian rings, whereas Noetherian rings strictly contain that class and then also have all other possible dimensions. All finite dimensions, I should say. Okay, so let's prove this. Okay, so let's start by assuming that A is Artinian. So if A is Artinian, we know it has dimension 0 from the last slide, so that's done. How do we know that it's Noetherian? To show that it's Noetherian, so recall that the Jacobson radical is equal to the nil radical. So in particular, if we were to take the product of all of our finitely many maximal ideals, this is going to be contained in the Jacobson radical, which we know is, sorry, this is the R notation. This is equal to the nil radical. And we saw the nil radical is nilpotent, which means that m1 through mn to the k is equal to 0. But what that means for us is that we can decompose A step by step. So A contains m1, contains m1, m2, etc., all the way down to m1 through m. I'll use a capital N here, which is equal to 0. And here I'm allowing repetition of these maximal ideals as factors, so that if you have, I just don't want to have to include powers in this description, but it could be that m2 is equal to m1. Just take as many as you need until you've covered k factors of each of these maximal ideals. Okay, so each of these has the structure of a vector space, right? So it's a vector space over the field A mod mk for some k. So each factor here, a m mod mk vector space. Okay, and a result proved in the chain conditions section is that a vector space is Noetherian and Artinian if and only if it's finite dimensional, and so the condition of being Artinian and Noetherian are equivalent. Okay, so this implies that each factor is Artinian if and only if Noetherian. Okay, so since we know that the whole ring is Artinian, that means that each factor must be Artinian, which implies that each factor is Noetherian. Okay, so I'll just write this out. So A Artinian implies each factor Artinian. Okay, and we know that those are vector spaces, so that implies that that each factor is Noetherian, which implies that the whole ring is Noetherian. And you can use direct sums or anything like that, composition series, to convince yourself that these if and only ifs are true. Okay, as for the other direction, suppose we're Noetherian of dimension 0. Okay, so let A be a Noetherian ring of dimension 0. Okay, so in particular that means that every prime ideal is maximal. It also means that every prime ideal is minimal. Okay, so we know that in a Noetherian ring we have primary decomposition of ideals. So 0 has a primary decomposition, which means it has finitely many associated primes, minimal primes. So 0 has finitely many minimal primes. Okay. But given that you have finitely many minimal primes, since you have dimension 0, this means you have finitely many maximal primes. Because every prime is both minimal and maximal. Okay. The intersection of all of the primes, i.e. the maximal primes, contains the product. So we can write m1 up to mn is contained in the nil radical. And there's a result that the nil radical of a Noetherian ring is nilpotent. So this implies, so since n to the k is nilpotent, that implies that this product, which is contained inside, must also be nilpotent. But then using that this is nilpotent, so we can again form this composition series. A contains M1, contains M2, M1, M2, etc., down to M1, Mn, which is 0. And by the same reasoning as above, same reasoning implies that A is Artinian. Okay, so we've proved now that any Artin ring, that the set of Artin rings is equivalent to the set of dimension 0 Noetherian rings. Okay, but if you don't require that the ring is Noetherian, then just because something is dimension 0 does not make it Artinian. And here's an easy example of that. So take R to be the ring x1, x2, etc. And now we're going to take S to be the quotient of R by the ideal x1 and then x2 squared, x3 cubed, then this ring is dimension 0 because it only has one prime ideal. Okay, so this has only one prime, namely the prime generated by all variables. So x1, x2, etc. How can we prove this is the only prime? Well, take any p in S prime. Well, since every variable has some power which is quotiented out by this, which is quotiented out in the construction of S. So the fact that xk to the k equals 0 implies that xk is in P, okay, because otherwise it wouldn't be prime. But that means that, so let's call this M. That means that M must be contained in P, but M is maximal, as you can see by taking the quotient. So M maximal implies M equals P, so this is the only ideal, the only prime ideal. So this is dimension 0, single maximal ideal, so it's local, but it's non-Noetherian because it's got this ideal generated by infinitely many generators, and it's obviously not Artinian as well, because every Artinian ring is Noetherian. And if you wanted to construct, for example, a specific descending chain which is not stationary, you could take, for instance, well, I guess x1 isn't the ideal, so let's make it x2 contains the ideal generated by x2, x3, contains the ideal generated by x2, x3, x4, etc. Okay, so Artinian means Noetherian and dimension 0. It's not, and both of those conditions are required. Okay, now let's consider what the powers of the maximal ideal look like in a Noetherian local ring. And we're going to consider how this relates to Artinian local rings as well. So let A be a Noetherian local ring. Let M be its maximal ideal. Okay, then one of the following holds. Okay, either, so first is m to the n is not equal to m to the n plus 1 for all n. Okay, so no consecutive powers of the maximal ideal are equal. And this would mean that, in particular, A is not Artinian. Or 2, I should say exactly one of the following holds, 2 m to the n equals 0 for some n. Okay, so some power of the unique maximal ideal of our ring is 0. Let's prove this. Okay, so suppose we have for some n, m to the n equals m to the n plus 1. Okay. So the first condition has now failed, so we've got to show that the second condition holds. Well, we know that m is the unique maximal ideal, so it's equal to the Jacobson radical. So we can apply Nakayama's lemma. When you multiply a module by any ideal contained in the Jacobson radical, if that keeps the module as it is, then the module must have been 0. So m to the n plus 1, well, that's equal to m multiplied by m to the n. And since m is contained in m is equal to the Jacobson radical, this means that m to the n, if we're saying that this is in fact equal to m to the n, then that means by Nakayama's lemma that m equals 0, or rather m to the n equals 0. So that proves that the second condition must hold. Now we can state the structure theorem for Artin rings, which characterizes all Artin rings. An Artin ring A is uniquely, up to isomorphism, a finite direct product of Artin local rings. Okay, so these, again, this is an Artinian ring with a unique maximal ideal. Okay, so we know that any Artinian ring only has finitely many maximal ideals. So if you localize at each of those, so localize at each of the finitely many maximal ideals, and take the product of the result. Okay, in particular, you'll have something like A is isomorphic to product of A localized at mi, where I goes from 1 to n. Okay. So let's prove this theorem. So first in one direction, namely that we can take any Artin ring and write it as a finite direct product of Artin local rings. Take a Artinian. Okay. What we know about A that it has finitely many maximal ideals. So A has finitely many maximal ideals. We also showed that because in an Artinian ring, then the nil radical will be nilpotent. So if our maximal ideals are m1 through mn, so we also know that since the nil radical is nilpotent, that implies that m1 through mn, the product, raised to the kth power is equal to the 0 ideal. Okay, well, if we have m1 to the k up through mn to the k, whose product is 0, and we also know that since each of these ideals are maximal, mi plus mj is equal to the whole ring for any I not equal to j. So this implies that mi and mj are coprime, and furthermore, their powers are also coprime. I to the k, mj to the k are coprime. So we can apply the Chinese remainder theorem. Which says that A is isomorphic to the direct product of A mod mi to the k, where I goes from 1 to n. Okay, so there we go. That's our Artin local. That's our decomposition of A Artinian into a product of Artin local rings. How about going the other way? Well, what do we mean? Obviously, if you have a product of Artin local rings, that's going to be Artinian. But the question is, so given A equals product of AI, where each of the AI is a Artinian local ring, each AI Artin local ring, is that the only way to write it? Okay. Can we write a different direct product isomorphic to this one? Okay, so obviously, you're able to shuffle the indices and things like that. But what we want to know is, are these Artin local rings uniquely determined by the ring that we're looking at? And indeed, they are. Okay, so we know that A is isomorphic to this direct product. So if we're looking at the kernel of each of the projection maps, so given the ideal AI, which will be defined as the kernel of the ith projection map, which takes A to AI, this implies that AI and AJ are pairwise coprime. They're coprime when I is not equal to J. Okay, and that's a consequence of the inverse of the Chinese remainder, the converse of the Chinese remainder theorem. So, given that we have these co-prime kernels, so let's look at each of the Artin local rings. So taking Qi in AI, the unique prime, and then we can let Pi be the preimage of that unique prime under the ith projection map. Okay. We're going to claim that Pi is a, or rather, sorry, AI is a Pi primary ideal. Why is that? Well, we know that the power of the maximal ideal, moving back up here, so looking at this result, so the fact that when A is Artinian, the power of the maximal ideal is 0, an Artinian local ring, I'm sorry, means that the power of the maximal ideal is 0, tells us that Qi to the n equals 0, because Qi is the maximal ideal of an Artin local ring. Well, that means that Pi to the n is equal to AI, because you're taking the preimage under this homomorphism. And what that means is that AI, as a power of a maximal ideal, is a power of a maximal ideal. It's not true for general prime ideals, but it is true for maximal ideals. So it's maximal ideal. So it implies that this is a Pi primary ideal. Okay, so what that means for us is that we have a collection, each of these AI is a different primary ideal associated to a maximal ideal of our ring. What else do we know about these AIs? Well, we know that the intersection of all of them is equal to 0, and they are pairwise coprime. These are both consequences of the Chinese remainder theorem. So this equation gives us a primary decomposition of 0, since each of those AIs is a primary ideal, which we just proved. And this fact tells us that this primary decomposition has each component isolated. So the second uniqueness theorem in the primary decomposition chapter tells us that each of these primary ideals will be uniquely determined. Uniquely determined. So any Artinian ring can be decomposed into this direct product of local Artinian rings, and that decomposition is unique, related to the primary decomposition of 0 in that ring. Okay, now let's look at one last concept, and this will be useful. We're not going to discuss discrete valuation rings, but if you look at the chapter of discrete valuation rings, this result will be useful there. We're going to consider a local Artin ring where its maximal ideal is called M, and it has a residue field k equals a mod m, then the following are equivalent. First, every ideal is principal. Second, the maximal ideal is principal. And third, the dimension of m mod m squared as an a mod m vector space is at most 1. Okay. So let's prove it. So 1 implies 2 is straightforward because maximal ideal is also an ideal. Okay. 2 implies 3, also straightforward because if m is equal to x, it's just generated by multiplying elements of a by that, but then also m kills m mod m squared. And mod m squared killed by m means that you can just multiply by elements in a mod m. Unless, of course, m is the 0 ideal, in which case you don't have any scalings of it at all, and it's a 0-dimensional vector space. So how do we get that 3 implies 1? We want to show that every ideal is principal, starting with this idea that the vector space is at most dimension 1. Well, let's consider what happens when its dimension is 0. So case 1, dimension over k of m mod m squared equals 0. Well, that means that m is equal to m squared. Okay. And that means that by Nakayama's lemma, if m kills m, and m is the Jacobson radical, if that's equal to m, I should say, then that means that m equals 0, since m is equal to the Jacobson radical, applying Nakayama's lemma. Okay. How about part 2 of that? Okay, so part 2 says that would have to consider the case where m mod m squared has dimension 1. Okay, well, let's take any ideal in the ring. So take A in A. So I know that since I'm an ideal in this ring, which has a unique maximal ideal, I'm somewhere inside there. But I also know that if it's an Artinian local ring, a power of m is 0. So assuming that A is not equal to 0 and A is not equal to the whole ring, then that means that there exists an R such that A to the R, just kidding, so that A is contained in m to the R, but it's not contained in m to the R plus 1, right? Because since it's eventually 0, at some point it's going to go from containing A to no longer containing A. The dimension being 1 tells us that this m must be a principal ideal, because if you didn't have that, you would have a higher dimension in that quotient. So now looking at A in m to the R, but not in m to the R plus 1, that tells us that there exists y in A such that y is a product of A and x to the R, because x to the R is the generator of m to the R. But since A is not contained in m to the R plus 1, this y, we want it not to be an m to the R plus 1, so that means that so y is not in the ideal generated by x to the R plus 1. So if A were a multiple of x, that would contradict y not being in this ideal. So that means that A is not in the ideal generated by x, but this is the maximal ideal. So if I'm not in the maximal ideal, that means I'm a unit. But that means that x to the r itself is in the ideal, right? Because if y is equal to ax to the r, you can just multiply by units on both sides. X to the r equals a inverse y, which is in the ideal A. So that tells me that A must contain x to the ideal generated by x to the r. And the fact that we have A contain, and this is equal to m to the r. So now m to the r contains A, and A contains m to the r. That means that they are equal, in which case it's a principal ideal. Okay. So that gives us our final result there, that 3 implies 1, so all of these conditions are equivalent. As for examples of Artinian rings, Artinian local rings with and without this property, so if you take z mod p to the n, for instance, this has this nice property because you have the maximal ideal p, p z mod p to the n. This is a maximal ideal. And every ideal is principal in here. And the dimension of pz mod p to the n over p squared z mod p to the n. This is just the same as z mod p. So dimension of, you can use one of the isomorphism theorems of rings or groups for that. This is dimension of z mod pz with over itself, z mod pz. So this is just equal to 1. Okay, so that's the first example where these equivalent conditions actually hold, but they don't hold universally. So another example of an Artinian local ring is, so take K to be a field, and you have K adjoin x squared x cubed mod the ideal generated by x to the fourth. So this has a unique maximal ideal, so x squared x cubed is the unique maximal ideal. It's not principal. So that means that the first two conditions don't hold. And when you take the quotient of the maximal ideal by its square, well, the square of this maximal ideal puts everything above degree 4, so that tells me that m squared equals 0, so this is just isomorphic to m, which has dimension 2. Dimension 2 over k. Okay, so this is an example where you don't have those equivalent conditions holding, and as I mentioned, this will be useful for discrete valuation rings and Dedekind domains. Okay, thanks so much.